that you understand the full storage stack. So we've talked about things that you should be aware of in your applications this morning, reasons why you should use I/O middleware, such as HCF5 and PNetCDF, to help deal with a lot of these complexities under the hood. And then absent that, we also talked about using MPIO directly, which again still hides a lot of this complexity from you so that you don't have to worry about it. And if you truly want to subject yourself to pain, you can write directly to the parallel file system using the POSIX interface. So we understand all of that, and then we understand the hardware and architectural implications of why all of this works the way that it is. So now let's shift gears and kind of tie everything together and talk about performance, I/O performance with the whole system in mind. So for the remainder of the time that we have, until 5, let's walk through some common pitfalls and things that we as operators of HPC facilities and resident I/O experts have encountered, and what these look like in the wild and how you can detect them, and what you can do to avoid encountering these yourselves, or if you have encountered them, you might have a eureka moment and realize, hey, I'm doing that terrible thing that Glenn is up there describing. Maybe I should stop. So it's the same picture that I showed before. This is the way the parallel file system works is your data is split up. And then I showed this diagram showing that one client, one compute node, can talk to multiple servers and get the performance benefits of multiple NICs and devices and things like that. But the reality is that the speed of light always applies. And this picture is a little disingenuous because if you look closely, there's a major performance bottleneck in here. And this is the situation that Rob described earlier, which involves, if you were to send all of the data from all of your MPI processes to the master process and then make that thing do the I/O, you're really leaving a lot of performance on the table for this very reason. So even if every one of these Lustre servers or GPFS servers might have a 100 gigabit network connection, if your client or your compute node only has a 100 gigabit network connection, you're not going to be able to get 400 gigabits a second of I/O traffic into your compute node or out of it. So instead, so that's one bottleneck. And the same applies if you flip the picture. So if you forget to stripe by default on both Theta and Cori, your file will only live on a single parallel file system server. And then you arrive in this case, where you're doing everything right from the application perspective. You're doing parallel I/O, perhaps with MPIO, but all that traffic winds up on one server because you forgot to set stripe and make sure that your file is actually spread out. On GPFS, this is not a concern because, as I said before, they do that whether you want it or not. And then everything in the middle also applies to this. So the many-to-one or the one-to-many are both problems. But there's also cases like I described when a server fails. A failover occurs, and then you wind up with one server that owns twice as many disks as everyone else because it's serving the disks that belong to its failed neighbor. And this can cause load imbalance, right? So while the vast majority of your compute nodes might be doing the right thing and talking to their own I/O server and writing their pieces of data out nicely, you might have some bits of your file that are doubled up on a single server. And true to pretty much every instance of parallel I/O, your total performance is limited by the slowest component within the system because your write call doesn't return until all that data is written down to the media. So not a good case here, but it is something that happens. And then both Rob and Quincy described this pattern where you might have misaligned data. And the way this works in practice is both of them said, both PNetCDF and HDF have this small header that's at the beginning of a file. And then even if your actual data is written in nice 1 megabyte stripes, this small header can shift everything such that every compute node, although it's writing down its nice 1 megabyte chunk, due to the fact that those chunk boundaries are essentially hard-coded by the striping of the file, every node is talking to 2 servers. And the way this works in practice to prevent data corruption is that, say, node 1 wants to write its stripe. It writes to server 0, which is fine. And then it writes to server 1 here. But while this write is happening, node 2 can't write its chunk to server 2. So it has to wait for server 1 to finish. And this just keeps happening down the line. So you've effectively halved your performance because 2 overlapping bits of the file that are belonging to the same stripe from the Lustre perspective can't be updated at the same time. So you want to avoid this situation. So what you really want to strive for is something where everything is nicely load balanced. This is exactly the same as with MPI communication. You want to make sure everything is talking the same amount of data. And again, as you scale up, you will often find the case where you have far more compute nodes than there are storage servers. So you want to make sure that even then, even though there is a bottleneck due to the fact that the storage system isn't running as fast as the aggregate of the compute in terms of network performance, you're still balancing that imbalance across all servers, so everything is running at its peak. So Phil introduced Darshan this morning, and this is where we actually look at some real Darshan logs that we've collected over the years from our users who've come to us with performance problems and pick them apart and look at what poorly performing I/O as a result of various issues actually looks like when you look at that PDF report that Darshan generates. So Phil showed a very similar picture to this. This is just the first page of that PDF. It's an eye chart. You don't have to look at it. I just wanted to remind you of all of the information that's included in a Darshan report. So you run the Darshan job summary script, and you generate this PDF file. You open it up either on your laptop or through an X connection, and you can see a variety of useful counters and graphs and things like that that are very easy indications that something is going wrong in your application. So one of the first pitfalls is a case where users think their application is doing something, but it turns out it's not doing that because there's a bug in the code. So this is an application where the user, they were opening 129 files. So there was one control file that was being written out and 128 data files. And they expected that every single one of those data files to have a 40 kilobyte header. So this could have been PNetCDF or HDF5, followed by a bunch of data. But when we opened the Darshan log, we saw that there wasn't just 128 of these headers being written. There were 512 of them, which you can see right here. Oh, so there's 129 files that were open. So that's what we expected. But it looks like there's 4 times as many headers being written out than what we did expect. And it turns out this was just a bug in the code. It was spaghetti code. As you know, I was once a grad student. I wrote my fair share of spaghetti code. This very easily could have been me. But it was just something where something was being written out redundantly because the code was unreadable. And then Darshan says, what you think you're doing is not what's happening. And this is why your performance is suffering, is because you're doing tiny IOs that you don't need to do. So this is a very easy way to detect issues like this. Go back in your code, figure out where that bug is, throw it through a debugger, and then you're on your way to better IO performance. Of a similar vein is redundant read traffic. So this is an interesting log where there was an input data set of 1.3 terabytes. This is a pretty big set of data that's being read in. And this is a 6,000 process job. So this is running pretty big, and it's using up quite a lot of resources. So the total input size we can infer from the Darshan log. So there's about 1,200 files. Each one's about a gigabyte, so 1.3 terabytes when you do the unit conversion. But if you look at actual bytes read out of the file, it turns out they're reading half a petabyte of data out of a data set that was only about 1 terabyte. So the only way this is possible is if you're just reading this file over and over and over and over and over 5,000 times. And it turns out this application was spending something like 99% of its time doing I/O, which is not a great thing. So this is disruptive to the application. It's also disruptive to every other application that's sharing the same storage system because your performance is preventing other people from getting peak performance as well. So this is generally not a good case. There are cases where you do this by design. For example, we see a lot of emerging machine learning workloads that are doing mini batching. So they're randomly rereading pieces of the file. And if that's the case and that's what you have to do, so be it. But there's ways you can optimize around this. So if it's unintentional, you can use collective I/O to just obviate this, and you're not reading from all over the place over and over. Or you can use a burst buffer so that you're reading, you're staging everything into Flash, and then you're doing this half a petabyte of read I/O to a Flash device, which is much faster, and you're leaving everyone else on the parallel file system alone. Another classic problem that we see quite a bit of is just essentially ignoring everything that we've talked about this morning. So we've been saying avoid small IOs, do everything nicely. If you can, just use collective buffering, collective IOs, use MPIO, use all the tools that we've taught you about. But we still see users doing things like this. And if you look at the histogram, which Darshan tells you of all the IO sizes, you can see that this application issued 5.7 billion writes to shared files that were less than 100 bytes at a go. So this thing was doing 100 byte writes 5 billion times. And if you look at the actual histogram, they were doing 1 byte writes. So writing 1 byte at a time. So you're paying network overheads. You're paying lock penalties because Lustre will only let you modify a whole stripe at once. I'm sure you're paying read, modify, write penalties at the RAID layer under the hood. And you're paying disk level penalties because those disks are not designed to do tiny things. So everything is going wrong in this job. So you see something like this and just stop what you're doing and consider, should I instead be using collective I/O or go back through the slides, find the YouTube videos, and just see if there's any of that stuff that you can apply here to figure out a better way to do this. Another common example, and this is something that has a lot of collateral damage in terms of other users being affected by the behavior of one user who may not realize what he or she is doing, is doing excessive metadata operations. And this is particularly painful on Lustre when all the metadata operations are serviced by a small pool of metadata servers. And this was a scenario where if you look at the number of opens and closes and other metadata operations this application was doing, it looks to me like they were writing, a ton, and every time they wrote, they would also stat that file to see what the new file size was. And this is an extremely expensive process. So if you can, instead of doing 200,000 files, which is what Darshan told us this user was doing, is there a way to use collective I/O, use something like HDF5, and really collapse that down? So instead of opening and statting 200,000 files, you're only opening 1 file, or perhaps a dozen files. This is also a good place to point out that there's a couple metadata operations that Darshan will tell you about that might not mean exactly what you think they do. So stat is just the call you use to see what is the size of the file, what are the permissions. And you would think that's a pretty cheap thing you do. You just say, hey, what's the size of this file? And you get it back, and you don't have to read or write or do anything. But on a parallel file system, the size of a file is determined by how many bytes are consumed across every single server that file is striped over. So when you stat a file that's striped, you actually wind up having to talk to a lot of servers. And someone, whether it be your application's compute nodes or the metadata server, is having to ask a whole bunch of servers, hey, how much data do you have that belongs to this file? Collect it all, add it up, and then send it back to you. It's a pretty expensive process. GPFS does things a little differently. It caches the file size within the inode. But again, that's not free. Someone at some point is still having to keep track of what's going on and how much data is spread out over all of these servers. Relatedly, and we'll talk about this in a minute, is that if you see a close call, like closing a file, again, should be pretty cheap. All you're doing is getting rid of a file handle. That can be deceptive because of buffered I/O and the page cache, which we'll walk through a demonstration of. You could actually see a close that looks like it's taking a long time, but what's really happening is that's when all of your writes to the actual parallel file system are happening. Because when you close a file, that's when you want to make sure everything that was written in memory is actually flushed out persistently to durable media. And then sometimes, you do everything right. You listen to the advice of Rob and Quincy, and you implement parallel HDF5, and you set up your collectives, and everything looks good. You run your application, and it is dog slow. And then you open up your Darshan file, and sure enough, 40% of your application's runtime is stuck in I/O. And you look at the histogram of what your access sizes are, and even though you said, I want to do the right thing and use collective I/O, Darshan tells you, it's not doing collective I/O, it's doing a bunch of tiny writes on your behalf. And this happened, and in fact, this was a problem that Quincy debugged, so he might be able to speak more authoritatively on it. But this was an issue. There was a parallel HDF5 application that was, the application developer did everything that they should have done, and things were going wrong. Right, so 40% of the wall time was spent doing MPIO, and the performance was abysmal. So this is writing 17 gigabytes at 25 megabytes a second. I can get faster speeds than that writing to a hard drive or a thumb drive, and that's clearly a problem. So what was happening after a bunch of debugging was it turns out there was a very subtle bug in this application code where they said that the collective I/O was going to involve a certain data type, and then what was passed to another part of the middleware was a slightly different data type. HDF5 saw that and said, this doesn't look safe to do because you said one thing and then you're giving me another. I'm just going to do the safe thing and not do collectives on this so that we're not potentially losing any data. Which meant that doing the right thing using collectives was disabled because of a very, very, very subtle type mismatch. After fixing that bug, suddenly everything is 40 times faster because collective buffering or collective I/O was enabled because the middleware realized it was safe to do, and everything was great. So instead of getting 25 megabytes per second, they were able to write it over gigabyte per second. And things sped up, whereas before 40% of the runtime was spent in I/O before, now we're down at around 6%. So this is a real testament to the benefits of collective I/O. I mean, if you get everything right and you're using it, you can stand to get a 40x speed up and not really have to do a lot of futzing around in your code to make sure everything is aggregated in a line. Just let MPIO do it, and it works really well. So those were just a taste of the things you might encounter in some Darshan logs. And if you're interested in taking a deeper dive, we have some of these logs. We're happy to share anonymized versions with you so you can go through and see what's going on. I also encourage you to take advantage of the demos that Phil mentioned this morning of 2 different versions of the same application that get very different I/O performance. Do give those a try. Look at the Darshan logs and see if you can figure out what was going on like we did here. And then I also want to take this moment to, again, plug Darshan. All the documentation is online. It comes with a set of tools that you can use to get a lot of insight into your I/O. But there's also a lot of third-party tools available and a growing ecosystem around Darshan because it is such a useful tool for debugging parallel I/O. So take a look at these slides, click some links as time permits, and get a feel for all of the things that can be added on top of Darshan to make it even more powerful than it is. So next, let's talk about actually measuring I/O. So Darshan is great because it profiles your application and what you as an application developer think you're doing versus what the application is actually telling the operating system to do. But it turns out that a huge component of the I/O stack that your data has to traverse to actually get to a storage device is completely obscured from the vision of Darshan. And this is kind of by design. I mean, if Darshan could see everything that was happening, it could also potentially see what other people are doing, and you don't want that. So this is a diagram that I found online that shows the complete Linux storage stack. And what I've circled in red here is the bit that Darshan's able to see and the bit that you control as an application developer. And the rest of the stuff is all kind of happening behind the scenes. So there's, if you're facing, if you're in the process of optimizing your I/O, and Darshan is just, it's telling you everything is right, but clearly something is not, you might be facing problems that are below the level of Darshan in the parallel file system. And it's often the case where it's just better to go ahead and run benchmarks. Take your application's I/O kernel, isolate that out, and just start playing with optimization parameters. And that's what we'll do here. But there are some tricks involved in actually effectively benchmarking I/O, and a lot of them might not be obvious because so much of this is completely hidden from the application. So I will use a tool called IOR. It is the standard parallel I/O benchmark. It's not an application, it doesn't really do anything useful. It just writes a whole bunch, and then it reads a whole bunch. And you can configure the patterns that it uses. And it has a bunch of storage backends. So you can do these I/Os using POSIX. You can pass all this through MPIO. You can also configure IOR to use PNetCDF or HDF5. It's just a good way for you to experiment with different I/O patterns and figure out how will this pattern behave on a given parallel file system that I have to use. So I will walk you through what I went through as a budding I/O expert before I was an expert when I was a graduate student of just trying to figure out how fast can I make my application's I/O go. So these tests were run on Corey's 700 gigabyte per second file system using 4 compute nodes, 16 processes per node. And when we run IOR very basically, so this is saying write 1 megabyte at a time and write 16 megabytes per rank, and then let every single rank write those 16 megabytes in 1 megabyte increments, and then repeat that process 256 times. And just, it's a very good I/O pattern. 1 megabyte writes in these nice 16 megabyte sequential strides is great. That's what you should be doing. But if you actually run this on Corey without any kind of optimization, the performance makes absolutely no sense. So it's a 700 gigabyte a second file system, but this is telling us that this I/O pattern only gets half a gigabyte per second write performance, yet the read performance is screaming fast. So the first thing I did was say, this guy Rob Latham, what does he know? He says don't use file per process, but it runs faster for me, so I'm going to use it. And IOR lets you run either shared file or file per process, and this -f flag just switches the mode to do file per process. So this gets rid of lock contention. It gets rid of all the worries about striping. It just writes one MPI rank, gets to read and write a single file. And then so just adding this one option, converting from single shared file to file per process, suddenly everything is screaming fast. So the writes went from half a gig a second to like 14 gigabytes per second, so that's great. But the reads went from screaming fast to like faster than the speed of light. So this is 4 compute nodes, and it's claiming that I can read at 260 gigabytes per second. And I know the network interfaces on these compute nodes aren't that fast. So this is something is happening here that I don't fully understand. And then after years of kicking this around as a graduate student who didn't understand how computers really work, I realized there's this thing called the page cache. And this is a part of every operating system's kernel. And what it does, it's an optimization. It uses the memory that's in your compute node that's not being used by applications just to store the data that's being read and written by applications. And generally, this is good because what it means is that if you're doing a whole bunch of small IOs, for example, they first land in memory. And then a whole bunch of those small IOs can build up in memory, and then it can be written out in one big chunk to the actual hard drive or SSD. So it's doing what collective IO kind of does, just in a non-collective, a non-distributed way. But it's fixing bad IO patterns where it can and making them into better IO patterns. Similarly for read, if you write a whole bunch of data, that data first gets written to memory. So when you read that data back, you read it directly from memory if those pages are still in memory. And it turns out that's what was happening. That's how we were getting faster than light performance, because I thought I was measuring file system performance when in fact I was measuring the performance of the page cache in the memory on my compute nodes. And the file system was never being touched. And it's very easy to do this. And this graph is just a demonstration of what happens when you scale up. So page cache, if you test at very small scales, it's very easy to accidentally just measure the page cache performance. But if you increase the size of the amount of data that you're writing, you suddenly hit a point where what you write causes a page to evict out of memory because there's no more memory. So that has to get written down to the file system. And then when you go back to read it back in, it's no longer in memory, so it has to go all the way back to the file system. And you can see with pretty stark contrast what happens when you exceed the amount of page cache available on a compute node. Your performance goes from faster than light to something that's a lot more reasonable here. So when you're benchmarking and you want to avoid this and actually measure what you think you're measuring, which is the file system performance and not memory performance, typically what you do is you shift your MPI ranks between the read and the write phase so that the data that's written by one node is read by the neighbor node, so that even if that data is sitting in page cache, the neighbor node can't see its neighbor's page cache and it has to read it from the file system. And Lustre or GPFS figures out how to make sure that whatever's in page cache gets flushed out of the file system so another node can read it back in. And again, IOR offers a very simple option, -C, to do that, and it does exactly what I described. It shifts ranks between the read and the write phase, or the write and the read phase, and it ensures that you're not reading from the same node with the same page cache that you wrote it all from. And so you do this, and suddenly the read performance goes from being faster than light to something that's very reasonable. 7 gigabytes per second from 4 compute nodes is pretty reasonable performance. However, that covers the read case, but what about the write case? I just said that every time you write to Lustre, that write actually lands in page cache first. So the question really is this write reflective of the write performance to Lustre? Or are we really measuring the write performance to memory, and then I'm not actually measuring what I think I'm measuring? So again, IOR has a neat option to make sure that you measure what you think you're measuring, which is -E. And what this does is it issues an fsync call at the end of your write. And what fsync does is it essentially forces everything that's sitting in memory that's not been committed to the file system to be flushed out so that you know that the data that you wrote is on durable media. And this is the difference between, say, if you want to time how long it takes to get from one train station to another. If you get on the train and then you start your watch and then the train goes, if you don't fsync, it's like measuring the time it takes for you to get on the train to the time the train begins entering the station. By doing an fsync, you're essentially measuring the time it takes for you to get on the train, get to the train station, and then also get off to actually where you want to be. So we add this -e option to ensure that we're f-syncing and we're flushing all the memory down to Lustre or GPFS at the end of this benchmark run. And in fact, the write performance that we got before was the true write performance. So these numbers are what the file system will give our 4 nodes. So we've got an I/O pattern and we've got pretty good I/O performance. So this is looking good. However, at this point I realized, maybe Rob and Quincy actually know more than me, and their recommendation of not doing file per process is a good one. So why don't we flip off that file per process that was our first way of trying to get better performance and see what happens. And much to my dismay, when you do that, you're right back to getting terrible write performance. What's going on here? Any ideas? All right, well, I will say that this is a mistake I make. This is a mistake that my colleagues at NERSC make. This is a mistake that I/O experts make. Forgot to set striping. Because this is a Lustre file system, you have to say, I want this file to be stored on multiple servers. Again, a very easy mistake to make. And in fact, Darshan will tell you what the striping of your files is. So if I was to open up the Darshan log for this benchmark, and it's actually in the hands-on repository, if you want to look at those Darshan logs or run this test yourself on Theta, you can. You will see that the file that I wrote for this top case was striped over only one Lustre server. And that's a very good indication that I'm doing something wrong. So I set striping to 8 OSSs instead of 1, so I get the performance of 8 servers, and I have my 4 compute nodes, and performance is back up to the multi-gigabyte range, and things are still looking pretty good. And there's plenty of optimizations to go from here, but this is kind of the process of, with your own application, where to start and what to think about and how to make sure that you're measuring what you think you're measuring. So that's what I just said. Make sure that you understand, that the difference between writing to page cache versus writing to the actual file system. And a lot of these problems, at small scale where you typically do benchmarking, you're hitting cache. And then when you scale up to really big, your real problem size and you're using a ton of memory and things don't fit in the cache, the performance is terrible. And it's often the case that it's because your benchmark was really not representative of what your application is doing at scale because cache effects don't really scale up too well. That said, it's not like page cache is evil. It does do a lot of great things. And here's an example of the BLAST application. I don't know if any of you here are bioinformaticians. We at NERSC run a significant amount of bioinformatics workload because we are affiliated with the Joint Genome Institute. And this application essentially reads through a file to figure out how much data each thread needs to process. And then it goes back and then takes its time rereading all of that data and processing it as it goes. So the fact that it's reading segments of the file over and over again means that page cache actually is awesome. So we get a huge speed up by using a file system with page cache enabled rather than just turning off page cache and saying, I want this to work against the file system directly. So there are plenty of cases where page cache is good. It's, the whole point of this exercise is to help you all understand that, how this works and how it will affect the measurements that you're doing when you're trying to figure out what the optima is for your applications. And so we talked about this earlier in the day, this problem where you have slightly misaligned I/O. And it's often the case where you're doing something bad, but it's just more convenient or it's more space efficient, or you have reasons to do the bad thing. And there's ways you can test it. So this is a case. And again, I believe this example is in the hands-on repo. So if you want to give this a try, you can perform this calculation, this measurement yourself, where we know we're doing misaligned I/Os because we have a small header. But we want to see, how much is this misalignment really hurting us? And again, as we said before, the misalignment results in a whole bunch of lock contention because what you think is a nice 1 meg stripe is actually being spread out over 2 servers, and every server is fighting with each other to write down those 2 halves. So there's an easy way to test this with IOR. Because IOR supports PNetCDF and HDF5, it's generating valid HDF5 files with that little bit of header that causes misalignment. So you just tell IOR, I want to write 1 meg data sets, and I don't really care about alignment, just do whatever the default is. And then you can also run it with a magical flag to say, I want to make sure every single one of my data sets is aligned on, say, a 1 megabyte boundary. So that's the difference between this top and bottom. You can pad out the header to make sure everything downstream of the header is aligned. And this graph in the top right shows the performance difference of doing this top case, which is unaligned I/O, and the bottom case, the same exact amount of data the same exact application kernel for I/O. The only difference is that you're issuing, in the bottom case, one of these hints, either the H5 pset alignment operation or these hints for pnet_cdf to tell it, I really want to make sure that this header is not screwing up the alignment on my data. And the difference in performance is very dramatic. So in kind of the worst case, you're losing more than 2x performance aligned versus misaligned when you're writing 1 megabyte blocks. And as I said before, you can try this yourself. The examples are checked into the Git repository, so I encourage you, if you're interested in this, play around and see what the performance difference is, alignment versus non-aligned. And this is exactly what's in those scripts. And you can give it a shot and reproduce this plot exactly if you so choose. So to wrap this whirlwind tour of performance up, we're going to look at an even bigger picture. So we've talked about what Darshan can tell you about your application, whether it's doing something right or wrong. And we've talked about how you can observe the actual performance when you actually issue I/O all the way through that deep I/O stack. But it's often the case that you do all this, performance isn't what you think it is, and you don't really know why. Is that because you have false expectations about what performance should be in this file system? Or is there something truly wrong with either your application or the file system itself that's causing performance to be degraded? So an analogy that we like to use is, if you look out your window in December and you see snow, that can be either normal if you're here in the Chicago area, or it could be, a freak of nature. The world is coming to an end if you live where I live in Berkeley, California, where it hasn't snowed since the 80s. And, in the abstract sense, snow is snow, right? But you need to have this greater context of, is this really strange, an extreme event that should not be happening? Or is this just, the normal state of the file system being slow? So actually understanding this bigger picture is pretty tricky. So Darshan gets you a picture of what's happening on the compute nodes, but it doesn't really give you a whole lot of insight beyond that because it doesn't have that vision into what's happening throughout the entire I/O stack and all the different components of the storage subsystem. So what do you do in this case is, you have to look at all of the different tools and pieces of the puzzle that stand between you and your data being stored persistently. And the sad thing here is that every I/O subsystem, every parallel file system is slightly different. Every center operates its own preferred set of monitoring tools that can tell its operators the health of all the different components, whether it be the I/O nodes or the storage fabric or the Lustre OSSs or NSD servers, or the actual disks, the RAID LUNs, things like that. And these are just some acronyms and some scary-looking tool names that make sense to anyone in here who's an I/O expert, but looks like gobbledygook to anyone who's actually doing science. And so it's frustrating for a user because you have to be really an I/O expert to make any sense of the output of these tools. And every time you move your application to a new center, you've got to figure out what tools they're using, what they've got. You have to figure out where it is, and you have to figure out how to interpret what the numbers that are coming out of it actually mean. So a project that we've been working on, and a number of centers around the world have been working in parallel efforts, is to look at this performance problem in a very holistic way. So rather than rely on some expert in the basement of NERSC to understand how all these tools work and how to interpret the data that's coming out of them and how to connect them all, and then finally answer that ticket 2 months later saying, your I/O performance was bad this day because a disk drive had failed. We'd like to approach this from a perspective of, build a layer of abstraction above all of these tools so that users can write very simple tools on top of things like Darshan or on top of all of these one-off tools that know how to monitor individual components of this complex I/O subsystem so that you can answer these questions yourselves without having to be I/O experts. So a project that I'm working on in collaboration with Phil is called TOKIO, the Total Knowledge of I/O framework. And what this boils down to in a very pragmatic sense is a Python library that actually understands how to talk to all these different tools, and it does so in a way that is layered, so that you can write an analysis application that has a call that says, for example, tell me how much traffic was hitting the parallel file system while my job was running in total. So it's not just my job, but what everyone else is doing. And you can take that tool and run it at NERSC. You can run it at ALCF without changing a bit of code. And the TOKIO framework under the hood knows how to talk to whatever tools are in use at that center to get that information, convert it into a consistent format that always means the numbers mean the same thing regardless of where you run it, and actually answer the question of, like, how much were other people interfering with my I/O when my job was running? And so this is a pretty powerful framework. So we've cooked up a couple of example analysis tools that are built on top of this framework, the first of which is called UMAMI, which is the Unified Monitoring and Metrics Interface. And what this amounts to is it's a tool that just talks to every single monitoring tool that is plugged in throughout the I/O subsystem and tells you what's happening over, while your job is running. And then you can also ask it, what was happening the last time my job ran, or the last time before that. So you can go back in time and get an idea of what a baseline definition of normal is for all these different parts of the I/O subsystem, and then return that time series of how your performance has evolved over time, as well as how all of the other things that are in the I/O subsystem were behaving over time. So this is an example where performance, which is measured straight from Darshan logs, is plotted over time for the same application that was running over the period of a few weeks. And then coverage factor is essentially the ratio of how much I/O my application did versus how much I/O everyone else was doing to the file system. And I can do this by talking to file system specific monitoring tools that are living on the back end of Lustre or GPFS. And then you can get an idea of, a 1.0 means I was the only one using that file system. And anything lower than that means that someone else was also doing something and consuming some of the bandwidth that the file system was delivering in aggregate. And then you can also look at things like, what was the CPU load on the servers that my files were being striped over? And you can get an indication of if something crazy was happening. Was there a RAID rebuild that was using up a bunch of CPU cycles? And you can also look at health of bigger picture items, like how full was the file system? And as you pointed out, you had to defrag hard drives way back when hard drives were commonplace. And in fact, defragging or fragmentation of Lustre is a major performance issue. And as you increase the fullness, there's fewer free blocks for you to actually write your data to on a Lustre file system. So it just takes longer for the file system to find an open block somewhere that it can write to. So as Lustre file systems fill up, they just get slower. This is just the way that Lustre is. And so you can also plot the fullness of the Lustre file system at the same time that your job was running. So zooming in on this, this was an example where actually a good thing happened was, we were running these applications every day. And then one day the performance of the application was just awesome. It was faster than we had seen it in a long time. And normally you don't, look a gift horse in the mouth, but this is a case where, being I/O researchers, we want to know, what was happening here, and can we do this again? Like, how can whatever was happening to make this good, can we make it even better? So we made an UMAMI diagram of this, and what we found was that, on the day when the performance was awesome, which is up here, the contention on the file system wasn't particularly low. It was within the interquartile range of all the past runs that we've done. But the CPU load on the Lustre servers was abnormally low. And then the question is, well, why was it high in the first place? And then we looked at the fullness of the Lustre file system, and it turns out that the fullness dropped precipitously at the same time that our performance skyrocketed. And then we went and talked to Tina, who was one of the system administrators at the time, and we said, Tina, what's going on with Lustre? And she's like, oh, I just started a purge. It was over 90% full, so I just started cleaning up data. The file system got emptier, and suddenly everything was awesome again because every single write wasn't having to scavenge the few free blocks that were scattered all over. Now, as someone who works at NERSC, I'm not proud to say that we wound up in this situation where the whole file system was so degraded because it was so full, but these are things that happen. And this holistic monitoring approach allows you, without any particular knowledge of, if you don't know Tina like I know Tina, you still have the ability to infer what might be happening using tools like this. And then another tool is this thing called, well, it's not written here. I'll get to that in the next slide. But one neat thing that Darshan can do is that if you write a bunch of files with Darshan, it tracks essentially how much time was spent writing those files. So you can actually calculate what the I/O performance for each individual file was. It also tracks the Lustre servers over which that file was striped. So you can think about correlating these two. And if you know that only a subset of your files when your application ran were really slow, you can start looking at all the OSSs over which those slow files were striped. and you can start picking out common ones. And we call these straggling OSSs. These are a common occurrence in every parallel I/O system because one slow server will slow down the entire write operation because the write doesn't finish until the last bit gets committed down to disk. So we built this very simple tool called Darshan bad OST, and it just opens up a Darshan log and then looks at all the files, what their performance was, and then looks at all the OSTs over which that file was striped, and it just does a very simple Pearson correlation to line up files that behaved very poorly with OSTs that kept appearing when performance was really poor. And if you run this tool, it literally prints this out. It says, this OST looks unhealthy. So instead of having to call up Tina and say, is something wrong with the Lustre file system, and then they have to open up a bunch of tools and start looking at what all the different servers are doing, Darshan has the ability to just go through and some very simple statistics say, this thing looks really suspicious. You might want to ask Tina what's going on, send her a ticket, and see if she confirms that something bad is happening. And this is actually it happens frequently enough that in cases when you know that you're going to do a full system job and you really need peak I/O performance, you can run a test like this and identify slow OSTs and then say, hey, Tina, can you disable this OST for a while so that my file doesn't touch it so I get the best I/O performance I can get? Or you can manually set Lustre striping such that you stripe over every OST other than this bad one. And then your whole I/O performance is slightly slower than if you used all of the OSTs, but you're not slowed down dramatically by the fact that one of these things, for example, might be doing a RAID rebuild. So to wrap this all up in the last 3 minutes I've got, I/O subsystems, kind of the whole purpose of the architecture discussion that I showed before is that these things are really complicated. There's a lot of disks, there's a lot of servers, there's a lot of networks, there's a lot of software. Your application is just the tip of that giant graph of all the things that your data has to flow through. So really to get a complete understanding of I/O performance, if you really have a major I/O problem and you really need to get every last bit per second out of it, it's often the case that you've got to take a more holistic approach to this. And this involves using tools like Darshan to understand what your application is doing and get information about Lustre servers and how they match up with your files, for example. But also looking at all the tools that the facility has in production that can give you insight into what's happening behind the scenes, and then use a framework such as TOKIO to connect all that together so that the I/O expertise of how all of this stuff lines up is encoded into a framework so that you as a user doesn't have to be that I/O expert. And then at the very bottom here, I've got some links to TOKIO and Darshan again. I encourage you to have a look. And with that, I will welcome any questions. Yes?
In talking about writing the striped files, I'm interested, say I've written to a file and then I've added some padding so that everything aligns nicely. But then I want to transfer that file to something like my laptop or something. How does that transformation happen? Or maybe more to the point, would I have to do anything special so that I can read it like I would read any other thing?
No, you would not. So that goes back to this. So to you as a user, you see this top pane. You just see one big file. So odds are whatever tool you're using to transfer it to your laptop, whether it be FTP, don't do that, use Globus, but whatever tool you want, it's essentially a user just like you are. So it's reading this 4 megabyte file. It doesn't have any visibility into how that file is actually distributed. Rob said that POSIX is stupid, and this is one of those reasons. So to POSIX, that's the thing that makes files and directories look like files and directories. There is no notion of a distributed file in POSIX. So any tool that uses POSIX interfaces like FTP or Globus simply has no understanding of striping. And all of that stuff is buried under the hood. So you can't really interact with it in any standard way. You have to use magical Lustre or GPFS commands. But in the absence of doing that, it's just a file. And it just gets read off the computer and onto your laptop, just like any other file. Couple questions. Let's start at the top and work our way down.
So suppose I have some file that I need to be shared and visible to all the different compute nodes, but I also need to do lots of small reads and writes to it. Where should I put it?
That question has no great answer. So I will say put it in the burst buffer, but I haven't described what burst buffers are because I didn't have time. But essentially, there's no one size fits all. What you do with a burst buffer is you would make a copy of it into the flash. And I presume when you say you need it to be visible, you're really only doing reads, you're not doing writes. So this is kind of like a database then. So you're doing little, yeah. So don't use files as databases, especially on a parallel file system. That is one of the hardest workloads on the file system. I don't know, do my fellow IO experts have any better advice? If you have a file that needs to be accessed by a bunch of compute nodes, but it's essentially a database and needs to be updated kind of all over the place. Yeah, I mean, that's where caching, whether it be page cache or burst buffer or something, is really your friend. But you know, depending on how close together your updates are happening, I mean, you might wind up evicting caches all over the place, and there's no great solution to that. You would want to use a file system that's optimized for IOPS, and we don't provision parallel file systems these days to do that. Was there a question way in the back?
Yeah, my question is also about alignment. So let's say I have a 10 gigabyte file, and I want to move it to Lustre.
Mm-hmm.
So I know the directory I want to copy. I set the stripe count, stripe size, and then I do SCP and copy it. Will the alignment problem arise or not? Because the file I'm not writing using MPI, I'm just
Right.
copying it to a directory or a file that has set configuration for
Right.
striping.
So the alignment really only factors in when you're reading or writing, and it depends on what the pattern you're using to read and write that file is. So if you're using the CP command, that's actually horrible on many levels, because what CP does is, I believe it's serial. So for one thing, your 10 gigabyte file is being copied just by one thread, so there's no notion of using multiple threads to move it. It's also doing things in like tiny 4K or 32K blocks. And that's a function of just the way CP is. It's just not, CP is not aware of parallel file systems at all, because it is a POSIX tool. So, you know, there's tools that can do parallel copies, like MPI file utils, things like that, which will make it go faster. You say, you know, 10 gigabytes or so. If you don't mind waiting a few minutes, you know, don't bother. But if you're talking like a petabyte file size, you really want to figure out a parallel way to move it. And in that case, you want whatever that parallel data mover is to make sure that it's just copying, you know, 1 megabyte stripes that are nicely aligned. Were there other questions, yeah, Axel?
Yeah. So I had in my mind with Lustre and following program, if I have an application that really does write large chunks per node, and I do large striping, there is somehow, at least in Titan there was one, a limit to 256 OSTs that I can use in maximum as a stripe. Why is that overhead striping that comes in with metadata? Or?
No, so that's an old limitation. So the maximum now is 2,048 OSTs, and to my knowledge, there is not a Lustre file system in the world that has that many.
Okay, but there's no overhead of striping. Is there some synchronization?
Oh, well, so the issue is not so much that striping incurs overhead, but it's everything that you do to a striped file other than read and write it. So for example, like statting that file means that, you know, when you stat to get the file size, it has to talk to every single one of those servers to get that file size to give it back to you. So there's side effects like that. So if all you're doing is reading and writing, you know, stripe it the best way that you can. That said, striping can go wrong. So I pointed out some cases where like an OST is rebuilding and it's slow and you want to avoid these stragglers. Just statistically, if you stripe over the entire file system, you're kind of exposed to the performance of the slowest piece of that, you know, entire file system. So that's why in this example, you know, if I said, you know, I set the striping here to 8, not to 248, because realistically my 4 nodes can't use the full bandwidth of all the OSTs, but they will suffer from the slowest OST over which my files are striped. So there is some balance, and there is some reading of the tea leaves to figure out what the right stripe size is. And it's it varies based on how big your MPI job is. There's no hard and fast rule about this. So this is a case where you ask your facility help desk, what do you recommend for this type of file? Yeah.
So you say you use an 8 here for this example because you don't want to use the whole system because you might get a bad one.
Mm-hmm.
Is it doing something smart where it says, okay, this one's oversubscribed right now, so I'm not going to give you that one?
Sort of. So Lustre it's not completely dumb in the way that it does this. So like I said, as the Lustre file system fills up, it tends to slow down. So it will pick the most empty servers to stripe, the most empty 8 to stripe this. And that's not strictly true. It uses the fullness as a weighting factor, and then it uses a bunch of other heuristics, but it does try to do the right thing. That said, once your file is striped, that's where it lives. So if someone comes along and just fills up one of those servers later, there's not a lot you can do about that. Yes?
Very quick, 2 questions. I was wondering if the Darshan bad OST thing was specific to Lustre because the other things were not called OSTs.
It is, yeah.
Okay. But is there something similar for other types?
In short, no.
Okay. And then my other question was for the HDF5 type mismatch thing. Was there the one where there's bad performance because of the type?
Mm-hmm.
Was there a warning that someone was just like, it's just a warning, I can ignore that?
Ooh, Quincy, do you remember the details of that particular example? This.
No, HDF5 assumes you know what you're doing, and that's what you wanted, and it will do it.
Okay.
Until it turns off collective I/O because.
That's okay, right? We got the data to disk, and that was what you wanted.
So it doesn't even tell you like, hey, I know you asked for this, but like, no.
Well, there are, okay, so to take back that slightly, there are a couple of properties that you can query off your I/O operation that said, by the way, did I actually get collective I/O when I asked for collective I/O? And so you can look at that, and then if you get an answer that says no, you can ask it, well, why did you not do collective I/O then?
Okay.
So there's 2 properties for that.
Yeah, so this was a case where, my recollection is that the user just submitted a ticket and said, I have a feeling that my application is really slow because of I/O. And can you just tell me if that's true? And then it just so happens, because we leave Darshan on all the time at NERSC, unless you explicitly turn it off, you've got Darshan logs for every job that you run. And so we could find their Darshan log, generate the report, look at it, and be like, yep, your I/O is really slow. Let's figure out why. And then it was an iterative process of figuring out what exactly was happening here. Any other questions? Oh, 2 right here. So Marcus first.
For your I/O measurements, you have to flush your pages to the disk. And do you also have then to shift your ranks for the read?
You do, because flushing, so when you flush, you're not getting rid of those pages. You're just making sure that they are also persisted on disk. So it's the difference between a clean page and a dirty page. So a dirty page in memory has not already been committed to disk. And when you flush, you just turn that dirty page into a clean page, which is mirrored exactly as on disk. So it's still in memory, and when you read it, you still get it back from memory. So that's why you still have to do the shift. And yes, you had a question?
Another question on Lustre. I guess I used to have at some point about 10,000 plus small files in the directory, and that means it's really slow. So is that specific Lustre implementation at that facility I use, or it's in general?
It's bad in general for a parallel file system. So one thing that I didn't mention is that both Lustre and Spectrum Scale are changing pretty quickly. So what you may have experienced 5 years ago may not hold true anymore. But that said, it's really never a good idea to have millions of files in a single directory. But 10,000 is not the end of the world. I mean, I admittedly have done that. And it's not great. The problem is more on you. It's just hard to manage 10,000 files. Anything else? All right, so we have now 20 minutes designated for open discussion. So Phil and Rob, how did you want to do this? Should we all come up here and just kind of get tomatoes thrown at us, or are there any residual questions about anything that we covered today, or more detail? Or I've got some burst buffer slides we can walk through, or the world is our oyster. Well, okay, so there's a question.
Yeah, I just wonder if you have any comments on Darshan for non-MPI.
It's awesome. Yeah, so we're working hard on it. We actually had a meeting, like Phil said, on Tuesday to figure out how to get that merged upstream. So there is a prototype that exists. If you want to play with it, I'm happy to show you where it is and show you how to use it. It has limitations. It was a proof of concept at first, but yeah, the idea there is, specifically at NERSC, we're supporting a lot of non-traditional workloads like TensorFlow I mentioned earlier. We also have experimental data analysis coming from places like Slack. I notice there are a few Slack people here, which don't necessarily use MPI. They might be OpenMP only. They may use, protobuf and all sorts of crazy non-MPI interprocessor, internode communication schemes like TensorFlow does. And the idea there is, still be able to figure out what's going on with those applications I/O, especially since they're so data intensive. So otherwise, it is completely compatible with all these Darshan tools. Darshan log, the job summary works. All of these downstream tools work. It just generates a regular Darshan file. It's just missing the MPIO part because there's no such thing as MPIO. But the goal is to make everything work. So you can do tracing, you can do the full report generation. You could even do the bad OST analysis if you want to. Yeah, that's what we're hoping to do. Yes?
So this is sort of going back to your first presentation. How would you compare the way that sort of we do file systems in high performance computing to those of, like, say, the big data centers in cloud and that sort of thing?
Yeah, so that's a great question. The cloud, so you can run GPFS or Lustre in the cloud. And the company that essentially owns Lustre, WAM Cloud, has scripts that allow you to provision Lustre in Amazon, Google, and Azure. So you can stand up a Lustre file system if you want. The issue there is that it's extremely expensive, like dollar-wise, because you're spinning up a bunch of instances with a ton of flash in it, and that costs a lot of money to keep online. So what I'm told the workflow is, typically in the cloud for non-MPI, so these are more like the machine learning workloads, is that they'll store their data sets in something cheap like S3, but they can't operate there because applications, by and large, expect POSIX. They expect files and file systems. So they'll just hydrate files from S3 into a temporary Lustre file system, for example, or Node local file system, do all their work, and then serialize that whole file system back into S3 objects and then stuff it back in and leave it there until they need to process it again. And Amazon, I kind of pains me to say this because I don't want all our users to run off to Amazon, but they've shown a really nifty tool called FSX for Lustre that you say, give me a Lustre file system. It just provisions everything for you. You write all your data there, and at the end of it, you say, pack this up and store it in S3, and it automatically just moves into S3, shuts everything down for you, and the next time you need it, you just say, give me that Lustre file system back, and it just rehydrates the whole thing, configures it, sets it up, and it's just there. So it's really an on-demand Lustre file system that actually keeps your data, but you're not paying the full cost of it. So pretty cool. But by and large, they're relying on more scalable storage systems like object stores for capacity, and they only spin up the performance parts when they need it, just because it's very expensive to do that. Anything else? Any open discussion from my fellow experts up here? Putting you guys on the spot. So I guess we have a couple options. I mean, we could break early. So we have our dinner speaker in 15 minutes. Is that right? We could take a break, or we could talk about burst buffers, or we can just mingle. And for those of you who may be too shy to come and yell up at me in front of everyone or at any of our experts, come say hello. And sound good? Okay. Any concluding remarks from our esteemed organizers?
I hope you stick around in the evening. I hear you were here very late for OpenMP.
I know it's Friday night, so I probably won't be here that late as you were on Tuesday night, but we'll be around after dinner, and so come back and you can tackle your problems, canned problems, personal problems, problems tonight.